Okay, so this is the last lecture in here of the semester. There's still class next week, Monday, which is going to be the end term test, but this will be the last lecture. Let me get the lights. All right, so at this point we've given feedback to all of, I believe all of the posters. If you haven't seen the feedback in Canvas, you should go and look at it. If you know, for some fraction people we just said approve, or there's pretty minor comments. And when you're done with those, just send those to Chris Coleman via the instructions in the PDF of the project. So you put data mining posters in all caps in the title, and he'll find them all. If you got more, if you either got more extensive feedback, or you kind of were said, you know, this is pretty far from what we were expecting. You know, please take some effort to like change up the poster, and then feel free to send just me via email another copy of the poster, and I can give you, either tell you it's good or say, actually there's a little bit more you should do, you know, just in case. I know some of you already did that. That's great. And I think most of the posters now are going to be in great shape. Yeah.
What's the deliverable for the final poster on Canvas? Is it the summaries, or is this like a resubmission of the
I don't think there's anything on Canvas. So the final grade, there's like a 15 points out of the 100 project points will be assigned for being at the poster day and doing that. So the points will come from one, you have to, when I go around to the posters, at some point I need to have you explain to me something, and it can't be, I mean, not too, it's again one of these parts where if you do all the requirements, you're going to get all the points, right? But, so you have to give some explanation, some interactive explanation of your poster. You also have to write summaries of other people's posters to be there. And so those 15 points will be given on the poster day. So you should have a poster there, right? So someone from your group either should send it to Chris Coleman to make sure it gets printed, and if that, you know, so that you need to do that in order to get all the points, or if not, you can print it on your own. Some people have kind of gone and said, well, I'd like it bigger, or like it printed bigger, or I'd like to keep making modifications past that, and have gone and printed at Kinko's or something. It'll cost you like 50, 60 bucks or something. I don't know, it depends. But if you want to do that, you can go do that. If you want to just print out some slides, I think one group had two versions, one with slides, one without. But in the past, people have put up some slides. They don't look as good. You can do that in your own. But as long as there's something there on the poster day, you're going to get those 15 points. And you can get more than that. Again, they'll be voting on everyone's favorite poster. So, you know, you can earn, I forget how many bonus points you can get. In the past, it's been like at least 5 bonus points for getting the favorite poster. This can help your grade. So put some effort into those. Look forward to it. Yeah. So any questions on that, or the end of the semester? Question?
I kind of have a poster question. I'm sure we're not the only team who was told to put less text on our poster.
Yeah.
My concern there was in the project, it says like content. These are the 4 things we want to see on your poster. for not putting the problem, the key ideas, but, you know, so we were unsure what to do there, so we get rid of our text, that content's not on there.
Yeah, so I mean, having some, hey, so hi, nice. So it's fine to have a little bit of text there. Just like full sentences and like paragraphs are not the right way to do it. You can also have it so you have something to point to as you're describing it. So as I go around and look at the posters, I am going to want to like hear these things from you in the 2 to 3 minutes that you're going to have to explain it. And so I'm not going to read any text. I'm not going to have time to do that. But you're going to want to guide me through the poster as you're explaining that, and then that a corresponding part should be on your poster. So yeah, so like if you have, you know, if it's just there's a big block of text, you might get docked some points for that, right? But if it's a little bit of text, I'm flexible on it. So I'm just trying to tell you what will be most effective during the presentations. All right, so okay, cool. And then the last homework. Don't forget about that. But I think it should be similar in difficulty to the frequent items homework and time. All right. Oh, and don't forget to do your class surveys, especially if you're going to give me good scores on those. If you're not going to give me good scores, you can forget. That's fine. But I think there's lots of really great stuff that we covered in the class. We covered a lot of material, lots of great resources. So yeah, great. Okay, so the last topic today will be graph sparsification. Okay, and so this is another topic in like understanding, doing mining and stuff on graphs. The kind of again, we think we have some input graph, which is the vertices and the edges, and the goal of this is to say, well, these graphs can be very big, and these graphs can be a pain to deal with because of their size. And what we'd like is a smaller G prime that basically. So there are a couple of perspectives on this. Why is this important? Well, so there had been this view that the number of edges in these graphs, like as I was mentioning on Monday, that there are these models of graphs that they have these purely random edges where each edge was either it was there equally likely in this random graph model, and these were not quite the right model. There are these more models based on preferential attachment and other properties that are more realistic. And so another thought of these graphs is as they grew, that you would probably have some property that there was some constant where the number of edges would be roughly maybe this was 20 times this number of vertices. So think of on Twitter, if you follow someone or they follow you back, either way this gives an edge, and maybe on average, someone has 20 followers, and so then this constant would be 20, so for every 20 edges. Or maybe this would be 10 because follow back, they give one edge, and so that'd be an average 10 followers. So if it was 20 followers on average, then I guess those count both ways. Maybe this is only 10, but think of some constant there. How many friends you have on Facebook? That's probably larger. You probably, on average, number of friends maybe closer to something like 100. How many links are there on a web page? Right? Maybe that's closer to 20 on average. right? So one question is, what is kind of these right constants? How do we measure this per graph? Well, it's not hard to estimate this value or to count this value. If you have the whole graph, you can just keep a counter. But a better question is this the right model? There's some people who still think this is the right way to think about it, but another view is that the number of edges is the number of vertices to some power, so 1 plus beta. And then beta, say, is usually in some range 0.1 to 0.5. Okay, so there's some, it's the number of vertices. Every vertex at least has one edge, right? But then to some power, right? So it's not, you know, assuming that you don't have multiple edges doing the same thing, then, you know, this power is at most 2, right? So, you know, there's this sort of models, right? Well, let's look at some numbers here. Let's say the number of vertices is 1 million. Okay, let's say the number of vertices is 1 million. What is number of vertices to the power 1.1? This seems like, this must be huge, right? It's some polynomial of 1 million. This must be an unbearably large number. Okay, any guesses? Quick guesses, top of your head. Shout them out.
2 million.
What?
2 million.
2 million. 4 million. 1.2 million. Okay. You know, initially you might think, I would have thought it would be larger, but you know, it's only, this is about 4 million. Okay? So if it's not that much larger, this is actually a constant of 4. Right? I said the constant's probably maybe 20 or 100, and a 1.1, a million to 1.1 is only 4 million. Right? If I do 10 million, I think the constant's like 5. It's like 5. From 10 million it goes to 50 million. Right? So this isn't so bad. If you go to 0.5, now it starts growing fairly, it grows more. Oh, I've written this down, I forgot. What is, yeah, what is 1 million to the power of 1.5? What is v to the 1.5? Billion, right. Yeah, so this is 1 billion. So now this is bigger, right? The difference between 1 million and 1 billion in terms of storage, that's a factor of 1,000 difference, right? That's something else is going on here, right? So it's somewhere in between maybe kind of a constant 4 and a constant 1,000 in this space. And we said between 10 and 20, this seems reasonable, okay? But from a modeling perspective, so these numbers are about the same, right? So these, if you just look at one data set, you actually don't know, is it this model a constant times number of vertices or a power of the number of vertices? But what difference does it make in terms of modeling? Like, what does it tell you about these social networks? So, kind of this model, again, says as they grow on average, each node has more edges, right? So as they're growing, each edge gets more and more edges. Right, so as Facebook is much more likely that you actually delete someone from your friends list, this can That's kind of, you know, so you tend to, when you meet more people, you add more people, right? This actually seems much more reasonable. And if you think, that's probably true on the web also. Web pages tend to have more links. Our screens are bigger, or at least they have more resolution in them, so you can fit more on the screen. Pages tend to have like these headers on the top that have lots of links in the header. These count as links, right? I'm not sure if that's true or not, but this is probably true. I don't have any data to back that up, but that's my guess. I think this model makes more sense. If you're saying this model, then model that the number of edges is growing with the number of vertices, then you need to start about as the number of not been explored quite as much. Most of them has been to fix V and then reduce the number of edges. So reduce the edge set. So go down to have the same vertices in the graph. So have the same, say, number of people, but you want to reduce the number of edges. And so if this is saying that edges are growing faster than the number of vertices, then reduce the edges back down to something that is going to look closer to this. That's going to end up being the goal. Okay, and so there's been kind of, so there's been definitely some work in this area trying to do this. And if you talk to various people who've been developing these methods, they're kind of saying, we've kind of started from what can potentially be done. We're ahead of the pace of the size of graphs, but eventually these are going to become very practical and useful. We're going to talk about two versions of this right now. One is going to be general and mostly theory. And if you talk to people who do this, they say, soon this is going to be useful. And some of the other stuff, like with the matrix sketching or the streaming algorithms, on the data sets we ran in class, those data sets weren't big enough for those to be useful, but those are now useful. They say something similar is going to happen here as the graphs grow bigger. I have some doubts, but it may happen. But right now Facebook is already has 1 billion people on it, and I don't think they actually use these techniques. So the other view of it is going to be is more restrictive. We'll talk about planar graphs, or they don't exactly have to be planar, but usually, so we'll think about particular something that's useful in, or at least low dimensional. And a good example will be like road networks. And so these are going to be more practical. Some of the tools we'll talk about, I'll talk about what is known about them, and then I'll say what you'd actually do in practice to get them to work. Okay, but this is kind of fits in with some of the other things in class, and so this may be something to kind of keep in mind as possible going forward. Okay, there's another part of this story that I should mention before I go on. Remember I talked about that there was like this MapReduce and there was Hadoop. And so these were kind of these general purpose tools, and then there were these specialized tools that were these descendants of them that work for a particular type of data. One of the most common things within these, the specialized one, the big class of things, were things for graphs. And there are these packages, which are not exactly in this framework, but there's something called GraphLab. There's like Giraffe. I think it's how it's spelled. But this one I think is directly in the infrastructure. This one I think is linked to it. There's some version of, I think there's some version of Spark that works on graphs in some ways. So there's some specialized some of these things, and these are things that are very scalable in that they can work in parallel very, very often. And so there's been some of this stuff fits into dealing with when you have huge data, you may need to use this very parallel machinery. There's been kind of some pushback that's saying that if you're careful how you store your graph, you could for almost any graph that, maybe aside from the Facebook graph, any graph you can almost publicly get, you can do this just in the memory of one machine. So most of the graph mining or processing, if you're careful and you represent it very well. So this means that you need to be very careful how you store all the edges, right? If you have a vertex, you want to say store the edges. You don't want to store it as a matrix really, it's going to be very sparse, but you want to just maybe not store the edges directly, but some compact representation of it. You can get these to fit on one machine, and then you can run these algorithms by a few iterations of something. So think of doing PageRank, and you're doing this by just doing this power method. You never actually densify the matrix, you always keep around something sparse. And so for some of the stuff you can do, you actually don't need this very parallel system. But these require less careful implementations, and so a lot of people still use these packages for dealing with large graphs. But they may not give even that much of a speed up, even though you may have 10 or 100 times more machines. Okay, so I just want to kind of give some context to this before I dive into some of the actual techniques. So I think these techniques, they're out there, they're in discussion. When you talk about large graphs, this is often what people talk about, so I think you should know about it. But I think you should also be aware that they may not, the other things I think we taught in class have all been kind of, they're clearly used someplace. And so some of the stuff I'll talk about first, it'll map to similar things in the rest of the class, but I don't know if they're actually kind of used in the general setting with graphs very much. But okay, so that's the caveat on this. Okay. Okay, so now, ignoring this, tell you that you can not worry about it too much, but just to give you the general picture, because there's some really cool math that goes on here. The idea is now I want to go from a graph, and where I'm going to think that the number of edges is going to be something like the number of vertices to say 1.5. And I'm going to reduce this to a graph G prime, which is going to have the same vertices and another edge set prime, where E prime is going to be a subset of the edges. And I might change some weighting on these edges, and I'll describe that. But in particular, you're going to have E prime is going to be some constant times the number of vertices times log space here times, so some constant number of vertices times log of the number of vertices. Okay, so this log is going to replace this vertices to the 0.5. Okay, so just give you a picture of what's log base 2 of 1 million. What's going to be log of 1 log base 2 of 1 million? It's going to be about 20. Okay, so and usually these logs are going to be log base 2s. Maybe it's a log base E. It's a natural log. It's going to be about the same. What is that? Let me just put this in 2 point. That goes down to like 13 or 14. Okay, so So we're still getting about a constant 20, and then there's this other constant here, which is going to depend on how accurate your answer is. This constant is going to be, and actually this log I'm actually not so worried about, but this constant is going to be 1 over epsilon squared to get epsilon error. So we're going to get some, if you get 10% error here, you're going to get a factor of 100 in front of here. So a lot of the literature says, let's not worry about this constant, but actually for a lot of the things that you want to do, you might actually need this 1 over epsilon squared here. So, okay, so now, now that you must be very excited about these techniques, let me just tell you, so there's some kind of cool thinking that goes into here, and you'll see some cool structure of the graph in the process. Okay, so the idea is that the basic technique is going to be called edge sampling. And so this will work within kind of within a pretty good bound of the best you can do. There's some much more complicated algorithms that you can run, but this edge sampling is going to work pretty well. Basically, you're going to sample each edge. We'll call this Eij. This is the edge between Vi and Vj into E prime, right? So you keep it with some probability Pij. So, and you do each of these independently. So you're going to just sample each edge independently of each of the other edges. They're not going to have the same probability. You're not going to sample them IID, but they're going to sample each one independently with some probability. And so there are certain edges which are going to be more important that you want to sample more with higher probability. Okay? And so this is where you kind of get to see how this interacts with the structure of the graph. And so the prob is going to be equal to the minimum each edge I'm going to sample with this probability, and so basically each vertex I'm going to keep around t edges. And t is 1 over epsilon squared log of the number of vertices. So it'll turn out to be the right number, and we'll see where that comes from. And so it means that the edges which are connected to vertices that have very high degrees, so they have a lot of edges, you sample those less frequently. Whereas vertices that don't have a lot of edges, you want to sample those much more likely. And in fact, if a vertex has less than t edges, then you want to sample with probability 1, which means you always keep it. Right? So let's say t is going to be like 5. Right? So I want on average every vertex to have 5 edges. If the vertex has fewer than 5 edges, then I always am going to keep all of its edges. Okay, and the reason for this is if it becomes disconnected, then it may really change the structure of the graph. Right? So if it has small number of edges, these edges are going to be very, very important. Okay? And so kind of the size bound is you're going to be able to say that the expected number of edges, or the expected number of edges, so the expected value is going to be t, is going to be bounded in t times the number of vertices.
That's E prime.
Yes. E prime. Okay, and so then if I set t this way, I get the size bound that I said I was getting. Right, so I no longer am growing polynomially in the size of the number of edges. Okay, and to see this is actually pretty easy to see. I basically assign every edge to the vertex with the smaller degree. Okay, and so then the probability that it's kept, okay, is, and then for every vertex, I look at which of those edges are kept, and the probability is kept is going to be t over its degree, right? So the expected number for each vertex is then going to be at most, say, its degree times t over its degree, right? So this is for each, so I assign at most this many edges to the vertex vi, and then I keep it with probability this, because I assigned it to the one with the smaller degree. And so it's, unless it's 1, and that's the case where I have less than t vertices, otherwise I keep it with this probability, and so this is equal to t. Right, so the expected probability, the expected number of edges per vertex that have been assigned to it is going to be at most t. Okay, so I'm getting the right expected number of vertices that I want here by doing this. Okay, and I'm keeping for vertices that have a small number of edges, I'm keeping almost all of theirs or almost all of theirs with lots of edges. Those are the ones where I can throw away. So you can think of these dense parts of these graphs, I can, it's easier to throw away these vertices. Okay, but if I do this, I'm going to lose some information, right? So let's say I have some graph that looks like there's some pretty sparse version of the graph over here, and then I connect it to this very dense graph here, right? There's some very dense part of the graph. And so this part is the one where I can throw stuff away. But if I throw stuff away, then it means that it no longer is going to look as dense. I've kind of lost this information. So I need to do something a little bit more. I need to set the weights of these edges. So basically what I'm going to do is I'm going to set the weight of an edge I keep equals 1 over pij. If kept, and it's 0 otherwise. Okay, so if I keep it, and I keep it with probability 1, so initially all edges essentially have weight 1. If I keep it with probability 1, this is still 1. If I keep it with probability 1/2, then it gets weight 2. If I keep it with probability 1/10, it gets weight 10. Right? So if it's part of this graph that's very well connected and I threw away a lot of edges, I'm giving that weight back onto those edges. And so this means that essentially the total weight of the graph is going to, an expectation, stay the same. So I'm not changing the total weight of all the edges. And so then, okay, so now if I reduce the graphs this way, what properties am I keeping? Right? What are the properties I'm keeping? It's going to have some property that this is going to preserve the cuts in the graph. Okay, so now if I to write notation before in G, all the edges have weight WE. So for each edge in the graph, it has a weight WE, and each edge in a prime has weight WE prime. Okay, so and these are the new weights here. So these are by default always going to be 1, but in general you could start with different weights, and then you could factor, and then this changes a little bit where the degree is going to be the sum of the weights instead of just the sum of counts of 1. Right, and all of this is going to go through as the same way before. So you can think of these as always being 1. Okay, and so now the property I want to have is that I will consider remember from spectral clustering lecture, is that a cut is going to be 2 subsets of the vertices where S union T is equal to the full vertex set, and S intersect T is the empty set. So this is a cut. And what I want is for all cuts, I want to have the property that if I want to look at all the edges in the cut, I think this is going to be epsilon times V. Okay? So I want that the weight of all the edges that I cross in the cut is going to be about the same. So this is what this epsilon is going to mean. And so if you are going to reduce the edges, you basically need, to get this property, you basically need to have T at this level here. So you need to have, T is going to need to be 1 over epsilon squared log of V in order to get this property. So if you want to preserve these cuts, remember these cuts are basically what you're looking for in things like in spectral clustering and in detecting these communities. So if you're doing either of these operations, then you basically, you can't really reduce the edges that much in order to get a good approximation to these cut properties here. Now this holds for all cuts. If you just cared about any one cut, you could probably do better. You may not know what that cut is. You may not know what that cut is ahead of time. So if you do this you randomly choose them in this process, then with some probability, this property is going to hold, and so essentially you then believe you could still run spectral clustering or define these communities in the graph. But you have to, there's an upper bound, and I think there's essentially, let me think, there might be, so with random sampling it's not going to work, but there is I think there's a technique that you can get rid of this log V here, but you still need this 1 over epsilon squared term. And I think this is really the killer. Really, remember, this may be about 20. This may be, if it's 10%, which is probably not enough, you need this to be 100. If it's 1%, then this may be 10,000, right? So, this is the term which is kind of stuck around. So a better way to think about this is that if you have some abstract graph and you want to reduce it and then run your spectral clustering or you find your communities on it, you're probably not in luck. It's probably not going to work that well. So in general, it's going to be tough to do this unless you start with a really, really dense graph, and then it becomes somewhat interesting. Okay. Great, and so this should look somewhat like this road sampling technique for matrix sketching. And that technique is actually is actually fairly useful in the matrix sketching setting. You can implement it very fast, and at first approximation it does fairly well. And people actually use that approach. It's basically you need a really large number of these edges to really make this happen. Probably in practice, This is probably an overestimate of what it's actually going to be. You could probably get away with like maybe t equals 100, it would probably work pretty well. But your graph probably only has something like a t equal to the average number of edges per vertex is probably only going to be like 100 anyways. So it probably isn't telling you that much. Okay, I just want to, before I move on to the kind of more restrictive and practical method, there's a, this part of the problem is pretty well understood from what can be done perspective as I understand it. There's a more general version that's preserving the Laplacian of the graph. So remember, the Laplacian of a graph, you can think of it as this degree matrix minus the adjacency matrix. So this one is stuff on the degrees are on here, and the rest is 0. And then the adjacency matrix is, so edge EIJ is 1 if there's a connection. Otherwise, it's 0 if there's no edge. Right, and we looked, and this is the, I guess this was the unnormalized Laplacian matrix. And so, more generally, what you'd like to do is to preserve the Laplacian G minus the Laplacian of G prime. You like this to be something like less than epsilon times V. So this property says that not only do you preserve all cuts, but you can get there's a slightly stronger bound you can write where it's 1 minus epsilon So you can actually supposedly get these relative error bounds here on these Laplacians of these matrices. And so if you can think of this x as being some way of kind of interacting with the graph, saying the value of something, and if the x, if this is all zeros and ones, then this is equivalent to a cut. So 1 is on one side, 0 is on the other side. But this is kind of saying you can have these more general ways of interacting with it, and for certain sort of analysis, this is what you actually want to preserve, and this is a little bit harder to do. There's a way of sampling this. There's you can still sample the edges, but then the probability you sample each edge is going to be proportional, is going to be some constant times the effective resistance. That's the right word. So the of the edge. So if you remember from your physics or your maybe intro electrical engineering class, you could look at a network and say there's some resistance on a bunch of these different edges in some system, and so there's less resistance here because you have because there are multiple ways you can cut across this, right? Whereas if you cut this, it completely disconnects the graph, right? So the effective resistance does a better job than just looking at the degrees of the individual nodes. So the degrees is something you can easily calculate really quickly from each vertex. But this is a little bit harder to calculate, the effective resistance. It basically boils down to either solving a system of equations, or you can actually, I think it ends up being similar to, there's some kind of related to like doing like the eigenanalysis of the system as well. So it turns out this is going to be roughly as, it's harder to calculate these values, but if you sample according to this, again, with t equals 1 over epsilon squared log v, then you're going to get this stronger bound here. Okay, so I just want to mention that you can get these sorts of bounds as well, and so this is still kind of like an active area. People are still trying to understand if we can do this efficiently. Yeah. So and there are people who think this I guess sampling. I'm not sure if. Yeah, the problem is calculating the effective resistance is actually pretty slow. So people want to do this as fast as before, and there's been work in trying to kind of speed up the runtime in doing this, but again, the bound is going to look something like this in the size. And so I don't know if this will ever become a very useful thing, but people who work in this area firmly believe that. Okay, so that's what I want to say about the general graph sparsification. It seems like something that would be really useful to do, but I think you really are going to lose too much information in many cases. So what can we do that's better? Let's assume instead, assume, okay, any questions on the general graph sparsification? Okay, so instead we're going to assume that these vertices have live in a metric space. And so then each edge, which is, there's some weight of this edge which corresponds, it's usually maybe is equal to the distance in this metric space between V1 and V2. And so in particular, it'll be useful to say that these vertices live in, say, R2 often. So they live in two-dimensional space. And so at least useful to think about it this way. You can often think about like points on a road. And so like if you're in Utah, there's Salt Lake City, there's Provo, this is I-15, and then you go up here to Park City and so forth, and off to Wendover and Vegas and so forth. Right? You have these road networks, and they kind of approximate this Euclidean distance. So it's a pretty good approximation to what's going on here. These things will often, some of these will work generally in a metric space, and if you have a road network and you have the travel time distance on these roads, this actually creates is a metric space in between the vertices. You can measure the distance between two things as the shortest travel time, as long as you don't worry about the symmetry of the travel time. If you make left turns, it takes longer than right turns and so forth, right? But if you ignore that, maybe it's just the total distance divided by the speed limit, then this gives is a metric. Okay? And so then we have a metric space on here, and now we want to try and sparsify this graph, and now there's a lot more hope for what we can do. Right? And this road network, like what I've drawn here, is actually a pretty good sparsification of what's going on, right? This is maybe 215. What is this? This is 80 going through here, and this kind of tells you how you get around the valley. There's other stuff going on here, but for a pretty good approximation, this is what it looks like, right? And so this is often, so we'll talk about as kind of the backbone of a lot of how these routing software actually works. So there's a lot more details that have gone into, but on the first level, when they first created these global kind of, you know, when you type into Google Maps or whatever, and you ask for driving directions, it tries to look at this map, and it really quickly needs to find the shortest path. It can't run a full Dijkstra on this graph, right? So what it does is it starts with this scaffolding, and it says, okay, if you want to go from Vegas to Park City, you would go like this, right? And then it might say, well, there might be a shorter route someplace else in there, but usually this is pretty close, right? Or you might start not exactly in Vegas, but you go onto the highway and then you come off of Park City, someplace like that. So what it does is it maps to some node on kind of this support structure that's been sparsified, and it finds the shortest path on here. And then often it refines it a little bit afterwards. So it starts here, and then there may be several levels of sparsity that have more and more depth, and it only needs to search locally. So how many people have taken the AI class? Okay, so good. So there's these search techniques, and there's like A-star search, right? So A-star search is when you want to search this large kind of space of things, and if you have a lower bound or on the optimal, you say, I have one path, and I know this will take, maybe 6 hours, right? Probably drive faster if you want to, but for maybe 6 or 7 hours, I know no path is going to take longer than that. So I don't need to expand my search space any further than that. If I don't need to start looking off of here, because I know that the distance from here to Park City plus this is not, if I go further out here, it's only going to take longer because I already have a lower bound. And this is not going to be a shortcut here, right? If I took 70 over and then up something like that, this is going to take longer, and I can really quickly prune out any path going this way. Okay, so you start with the sparsification and then you build up. Okay? Right, so this is one of the kind of applications of this. And so now the goal is going to be a little bit different. We're not going to be trying preserving these cuts anymore, or these Laplacians, which is some generalization of the cuts. Instead, what we want to do is to define a metric on the graph. So you want to go from, again, one graph down to a smaller number of graphs. And again, these are going to have the same vertices, but a smaller number of edges. You know, in this case, you may end up throwing away some vertices as well in these scaffolding, and then having a way to connect to them, but they're all implicitly there. And you'll actually, maybe you'll see exactly how this might work. You have this hierarchy here. And you want to do this so that you can define a metric on this graph distance. So you have some distance on the graph between two, so vertex 1 and vertex 2, and this is essentially the shortest, it's the length of the shortest path from V1 to V2 on G. Okay, so I want, so what I'm going to want is that G prime is going to now satisfy that 1 is less than so it's often written, again, with the T parameter. It's called this is going to be called a T spanner. So this distance is always going to be smaller. I'm going to sparsify the graph, So if I take out an edge I would have used, I'm always gonna, this distance will always have the shortcuts in it that I might miss. I might miss some shortcuts. But I'm going to, so this is always going to be larger, but it's not going to be too much larger. Right? And so you might have, say, t equals to 1, right? So it's always within a factor 2, or t equals to like 0.1, so it's within 10% of the cost. Right? And so these are the things that you're going to strive for. So a lot of the literature, when you get bounds like this, it's 1 plus epsilon. In this literature, it's 1 plus t. That's just, so if you see it, don't get confused. Okay, so, and when you're doing this, you want to have this property, and you want to minimize a few number of things. You want to have small number of edges. You want to have small total weight of the edges. So before, when the graph sparsification, we actually kept the total weight the same. Now we can get down to a smaller total weight. We can just throw away edges because we're not worried about cuts anymore. And then you want a small max degree. What you don't want is, you can actually, sometimes you'll actually change edges, or you'll add edges, or you'll start with graphs that have a lot of edges in them, and I'll explain why that would make sense. And you want the maximum degree to be small. So in a road network, this is probably not going to be a problem, because you usually most intersections have 3 or 4 degree. You see some with 5, but it's rare to have larger than this. But you want the overall degree to be small. So one of the things is this will often start, instead of a road network as the base, is that you may just think of, you have a bunch of points in the plane, and you have all possible edges. Right? So if instead I was planning some, I said, there was something horribly wrong with all of the roads in the U.S. Like, there was some weird acid rain, all the concrete and asphalt disintegrated. I can redo all the road networks. Now I just have these locations where people live and they need to go, and I need to build all new roads. I get to plan from scratch. What would I do over again? And if you look around the internet, you can probably find some people have fantasies about this and actually replan this, or they're trying to, you see these things where people are planning like a rail network through the US, which, I mean, like a high-speed rail network, probably never going to happen like the full US, because we're so much more spread out and mountainous than Europe and so forth, but people have dreams, or these are people who live on the East Coast who've never been out to Utah and say, yeah, let's just put a high-speed rail. It can't be that far, right? I think we're probably one of the last places to be on, one of the biggest cities to not be on the high-speed rail. I guess you could connect this to Vegas or something, but I guess Vegas and LA might get a high-speed rail soon. That's one of the next places I heard. Some Chinese investors, there's a new big Chinese casino, and they might put a direct route there. But okay, so maybe there's hope. But anyway, so you have these new data points, and you initially have all of these edges. Every edge is available here, right? And so that means that each vertex initially has, if there are n vertices, then there's n edges, and you don't want this. This makes planning really much more challenging. It's kind of a pain to deal with. You get these large edges is essentially what we were getting rid of in the graph sparsification. These are the problems in things like counting triangles. These vertices with a lot of edges on them are a pain. So we don't want a big max degree. Okay, good. So now this problem is going to be much more reasonable to do something like this. Just before I talk about algorithms, one more modeling issue which is kind of important. Is a road network a planar graph. Is a planar graph a good model for a road network?
There's overpasses in the road.
Yeah. It turns out that, you know, for a first cut approximation, get like 90% good, planar graph works pretty well. When you start getting lower and lower level, it starts to break down. These overpasses are a problem. You can get one way, but you can't, and these things are crossing over each other, and you can't you can't take the intersection even though it crosses, right? And so and another issue is like these there are these roads which are one way, these one-way roads in cities, and you know for inside of cities where they have like parallel one-way streets, I know like Salt Lake has 500 and 600. Hopefully it's not that confusing, but some cities, like a lot of their roads are one way because their streets aren't as wide. And so that creates some problems. It's worse when you have like these freeways that have feeder roads on them, but the feeders go only are one way on one side of the road and one way on the other, and it gets confusing. And so there's a lot of effort now. There's all this cool data from OpenStreetMaps. Where people, has anyone looked at this data? This OpenStreetMaps data? So this is kind of like a community crowdsourcing way of mapping all of the roads, right? So Google's, but they're owned by Google, right? OpenStreetMaps is an open source effort to do this, and I think it's now pretty good in the US. It used to be much better in Europe, but people would go and they would just bike with a GPS tracker on their bike and then upload it. And so we get all these traces of where people went on these roads. And then you try and figure out where are the roads from all these traces. And you really, if you start just doing a planar graph, it doesn't do a good job. You need to know which side of the road they're on and all these other issues. So it's going to be a pretty good approximation, but there's some modeling issues with it. So kind of keep that in mind if you get deeper into this. Okay, but for now we're going to ignore those issues. We're going to assume that, so let's now assume that V, our nodes